Hello everyone, this is the Laplace Patrol and we're here to help you guys understand a bit more about how modeling growth really works. In this case, we will be analyzing the US population. USA is one of the countries that has the highest population on Earth. As of right now, it stands at 328 million people. Over the past 200 years, we can notice a rapid increase in its population. For example, from 2019 to 2020, the population grew by 0.35%. However, is there a way that we can model this population growth? Yes, through different population growth modeling, we definitely can. First and foremost, I would like to introduce to you guys the exponential growth model. It was first discovered by Thomas Robert Malthus, an English economist, which is this guy over here. And if we were to look here at the bottom right side of the paper, we have dp over dt as the growth rate of the population at an instant, p is the population that is being studied, and r is the rate of increase per individual. According to Malthus, he said that in the exponential growth model, the population growth rate increases in proportion to the size of the population. By the name of this modeling type, you guys can infer that the graph would look something similar to the exponential graph. As we can see, as the time is increasing, the population is increasing as well, meaning that this is an exponential growth. However, what happens if we run out of resources? I bet this lady is thinking the same thing. This leads me to the next modeling type, which is logistic growth. It was first discovered by Pierre Velhurst, a Belgian mathematician. I really hope I didn't butcher his name, but anyways, moving on. Unlike the exponential growth, the logistic growth introduces a new variable, the carrying capacity. Velhurst stated that in the real world, as the population increases, there won't be enough resources available for the population to consume, as the population is going towards infinity. So Velhurst suggested that there should be a capacity, or other known as the carrying capacity. If, for example, in the exponential model, we said that r, or our rate of growth, it is independent of the size of the population, in the logistic model, we say we can modify r, so now it depends on the size of the population. We can see on the first photo that the population is only exponentially growing, while on the second photo, it starts to grow exponentially, and then it levels off as it's approaching the carrying capacity. I think we're getting onto something good here, guys. Okay, you guys, so last model I want to share with you is the Gompertz growth model, founded by the British mathematician Benjamin Gompertz, which is none other than this dashing young fellow over here. And actually not very different from the logistic model, Gompertz model agrees that there should be a carrying capacity factor when we're studying the growth of the population. However, as we can see on this picture over here, we can immediately tell the difference of the behavior of the population between the logistic model and the Gompertz one. The Gompertz model is modeled by the yellow curve over here, and the logistic model is modeled by the red curve over there. In Gompertz, the curve is smoother and has a smaller slope, suggesting that the population grows faster, while in the logistic model, there is a rapid increase over here, and then slowly starts decreasing as it's approaching the carrying capacity. So what do you guys think? Which one of these models would be the best choice to model the US population growth? You can pause the video now and give your answer, but theoretically speaking, I believe the Gompertz model would be the best choice, since the US population relatively has had like a smoother pace of growth. However, stay tuned because next we will see the mathematical explanation behind it. Guys, aren't you excited?
To start off, these are some data depictions of the US Census. On the right is a graph and on the left is a table with the data showing the US population every decade since 1790 to 2020. The horizontal axis is time in years, while the vertical axis is the population of humans. This graph helps to show us the population growth of the humans is most certainly not linear. Let's go over some models that can be used to depict and maybe even predict the human population growth rate. These are some potential population models. Based on the shape alone, the linear model seems like the worst. After taking a glance at the US Census plot, you can see that the population growth is not curved, is curved, and it's not linear. So that one isn't going to be accurate. Now, the exponential growth is an okay depiction based on the plot points. However, personally, I think the population growth will reach a carrying point capacity eventually, and the exponential growth model shows no sign of slowing down. However, the Gompertz and logistic models are the most accurate based on shape alone. They have a curve of fast-paced growth in the beginning, the middle starts to dull down, and towards the end, it looks like it'll eventually reach a horizontal asymptote. However, I'd like to mention that these are just assumptions based off the shape. Maybe the math will prove later otherwise. One way to help create these models is by utilizing the per unit population growth rate, or Ppgr for short. Basically, it's a measure of how much one person affects the population growth rate. If the population was expressed as a function of time, then the Ppgr would be 1 over the population times the growth rate. Let's go over an example to better understand the Ppgr. Say you're given an estimate that the human Ppgr is equal to 1/2 per year, with the reasoning that women are half the population and each woman can give birth once a year, contributing to a new member to society. Well, that would entail that each year the population increases by 50%, what it was the previous year. It's an interesting idea, but I think it's way too high of an estimate. Here's a graph comparing the US Census data in blue with a function that starts at the same population in 1790, just like the US Census, but it increases with a Ppgr of 1/2 per year. By the way, the blue dots are from the same data as the first graph, but they look a bit different because the scaling of the y-axis is it's a bit different to show how vastly different the two functions are, to show you how much the orange one changes from the blue one. If you think about the factors affecting the Ppgr, it makes sense that 1/2 per year is too large. If the Ppgr was 1/2 per year, then every woman on the planet would be giving birth to one baby every year, which isn't realistic. And we'd have to account for the fact that not everyone chooses to have children. And we also have to consider how many children each person will have in their entire lifetime. So if 1/2 per year is too much, let's estimate a better Ppgr. In order to find a Ppgr, we're going to go to the data on Excel. The Ppgr of 1/2, shown on the left table, has a percent increase of 150%. The table on the right shows the US Census and the percent increase from each year to the next. We can definitely use this information to help find a more suitable constant Ppgr. I found the average of the percent increase to be around 122%. Therefore, my estimate Ppgr is 1/5. This is a graph representing the estimate compared with the US Census. The US population is in blue, while the function with the Ppgr of 1/5 is in orange. You can tell it's not exact, but it's a better estimate than the first. In the beginning, the estimate is lower, but actually if you look towards the end, it looks like at some point the orange overtakes the blue. And if we were to extend the timeline, it looks like it would be too high of an estimate. So maybe a constant Ppgr is not the most accurate depiction.
Now let's go on to a mathematical analysis of Ppgr. As a reminder, Ppgr measures how much one unit of population, in this case one human, contributes to growth in the population. In order to find the Ppgr for each of our models, we need to use the equation Ppgr equals 1 over p times dp over dt. Now all we have to do is plug in the given dp over dt for each model. Thus, we can find that Ppgr for the exponential model is equal to r. For the logistic model, Ppgr is equal to r times 1 minus p over L. And lastly, for the Gompertz model, Ppgr is equal to r log of L over p. Now, to continue our analysis of Ppgr, let's consider each model if the population is very small. For the exponential model, Ppgr is equal to r, so the population does not affect the per unit population growth rate. When we consider the logistic model, Ppgr equals r times 1 minus p over L. So it is obvious that the population definitely affects the Ppgr. For this model, we also have to consider L. the limiting population, which is the maximum population. Since P is divided by L, and P is very small while L is a very large number, we can consider this fraction to be 0. If this fraction is 0, then we get Ppgr equals R times 1 minus 0. Thus, Ppgr is just equal to R. This makes the logistic model very comparable to the exponential model if the population is very small. Now for the Gompertz model, we again have to consider L the limiting population. In the Gompertz model, there is the fraction L over P. Thus, if P is a very small number and L is a large number, the fraction L over P has to be some number greater than 1. If L over P is a number greater than 1, then log of L over P must be greater than 0, because log of 1 is equal to 0. This means Ppgr will be R multiplied by a positive number. So, unlike the exponential and the logistic model, if the population is very small, it is not just equal to R. Now let's consider if the population reaches the limiting population. So we will take P equal to L. In this case, we are not going to consider the exponential model because the exponential model does not take P or L into consideration. In both equations, P and L are in fractions, and if L and P are equal, these fractions will equal 1. So for the logistic model, Ppgr will equal R times 1 minus 1, thus Ppgr will equal 0. And for the Gompertz model, Ppgr will equal R times log of 1, and log of 1 is 0, so Ppgr will again just equal 0. Now let's relate the findings from the past slides to the figure. In the figure, you could see that there is a linear slope, there's an exponential slope, and you could see both the logistic and the Gompertz models behave very similarly. When these models reach the limiting population, their slope flattens out. This means there's a horizontal asymptote at L, so the population will never exceed the limiting population. This is why Ppgr equals 0 for both of these models when P equals L. This does not make sense for the human population because our population will simply grow even when the Earth is overpopulated. Although there are many homeless and unemployed, because there is simply not enough space for everyone, our population continues to grow. This is why the exponential model is the best model to represent the US population. And the Gompertz is the worst model because, again, like the logistic, their slope flattens out at L, and also when the population is very small, the Gompertz model behaves differently than the logistic and exponential model, making it the worst model to use.
For the exponential model derivation, it begins with dp over dt equals r times p. This is an ordinary differential equation which is separable, which means that the function is able to be factored into the product of two functions with two different variables. To do this, you divide p by both sides, and then you have the 1 over p, dp, and then you multiply dt on both sides, so it would be r dt. Then you do the integral of both, which results with this. And then you want to do base e of both sides, so then you're able to get rid of the ln and p is by itself. Then you want to solve for the constant c, which is equal to p of 0, and p of 0 equals p naught. Therefore, the resulting equation is p of t equals p naught times e rt. For the logistics model derivation, you start with the equation dp over dt equals r times 1 minus p over l times p. This is also a separable ordinary differential equation, so you do the same process as the exponential model, and then you want to do the integral again. And in this case, you use the natural log rules to be able to do L minus P over P, and then you do base E for both of these again, which results in this. And then again, you want to solve for C when you use T equals 0, and since P of 0 equals P naught again, that's what the C would equal. And then you finish solving for P of T, and then this is the resulting equation.
Lastly, for the Gompertz model, the derivation begins with the equation dp over dt equals r times log base e, which is also the natural log of L of p times p. And again, it's a ordinary differential equation that is separable. So So you do the same process as before, and then you do the integral, and then you have to use U substitution to find the integral, and then that results in the equation P of t equals L times e raised to the negative log of e over L over P of naught times e to the negative RT.
In this slide, we are going to discuss regarding the parameter estimation using Ppgr. To estimate parameters using Ppgr, the first parameter to be considered is P0. This parameter represents the population when time t is equal to 0. For the above table, let us consider P0 to be equal to 3,929,214 for t is equal to 1790. In other words, the 0 year, that is t is equal to 0, is considered to be 1790, and the population at that time is 3,929,214, which is represented by P0. The year and population was accordingly selected since they are the initial values given in the table. In this slide, we are discussing regarding the methods to calculate Ppgr. As discussed in the previous slides, the three main models, that is the Exponential Model, Logistic Model, and Gompertz Model, can be used to calculate Ppgr. Before moving to the three main models, the first step of calculating Ppgr is Ppgr is equal to 1 over p times dp over dt. dp over dt represents the instantaneous population at a particular time. Now, the three significant models have three significant methods of finding dp over dt. For the exponential model, dp over dt is equal to r times p, where r represents the growth rate and p represents the population. In the logistic model, dp over dt is equal to r times 1 minus p over l times p, where in addition to r and p, L represents the limiting population. In Gompertz model, dp over dt is equal to r times log L over p times p. In conclusion, for the exponential model, Ppgr is equal to r. For the logistic model, Ppgr is equal to r times 1 minus p over L, since p and p got cancelled. And for the Gompertz model, Ppgr is equal to r times log L over p. Again, p and p gets cancelled. Note that contrary to the exponential model, logistic model and Gompertz model requires the population and limiting population in addition to the growth rate to calculate Ppgr, whereas exponential model only requires the growth rate to find the Ppgr. In this slide, we are discussing the conventional method to calculate Ppgr. The conventional method of calculating Ppgr was obtained from the handout published by Johns Hopkins Bloomberg School of Public Health titled Introduction to Population Projections. According to the handout, per unit population growth rate is equal to present population minus past population over initial population times 100. Present population represents the population for the year which is being considered. Past population represents the population of the year previous to the year being considered. Initial population represents the population for P0. In this slide, the graph represents the Ppgr versus P graph for the United States population data. In the graph, the blue dot has coordinates x, y, where x represents the population and y represents the Ppgr. Using the above data, a linear function y is equal to f of x, a, b can be obtained, where parameter a represents the slope of the line and parameter b represents the y-intercept. Neither the x variable nor the y variable have any units, since the x variable represents the population in numbers and the y variable represents the function made up of constant elements having no units. In this slide, we are discussing the method of calculating and plotting Ppgr using the conventional method. The table and graph on the slide
represents the Ppgr calculated from 2010 to 2019 using the conventional method mentioned in the previous slide. The solid line represents the best fit line. The equation of the best fit line represents the y variable as discussed in the previous slide, which is in the form of a linear equation. As you can see in the table, the first column represents the year, the second column represents the population, and the third column represents the Ppgr. Please note that the values for the Ppgr was calculated using the conventional method.
Another way of determining which model is the most accurate is by using the ordinary least squares estimator. First, we need to turn the exponential model into the slope-intercept form, and where P0 and R will be constants that we need to find. P0 is the initial population, and R is the growth rate. To determine what these values are, we must use the ordinary least squares estimator. The equation shown, where yi is equal to alpha plus beta times xi, is what the resulting linear equation will be modeled after. To find beta, you must use this equation, and to find alpha, you must use this equation. So after that was done, beta was found to be this, and then beta equals P0, so P0 also equals this. And then alpha was found to be this, and R equals alpha, so that's what R is as well. And the resulting equation was this. So now we will see what the graph looks like. This is what the resulting graph is. Another way of determining the most accurate model would be by using the nonlinear least squares estimator. However, we ran out of time and were unable to complete that.
To conclude, there were 3 different model types in order to represent the U.S. population growth. This includes the exponential model, the logistic model, and the Gompertz model. Theoretically speaking, the best model to illustrate the U.S. population growth for the past 2 centuries was found to be the Gompertz model of growth. This is because you would expect to have a limit in the population. However, through calculations and data investigation, the best fit to model the U.S. population is the exponential growth, due to the fact that our population will not stop growing even if we were to reach the carrying capacity. Also worth to mention are the observations made relating to Ppgr. As mentioned, Ppgr is the impact that a unit of population, in this case 1 human, has on the overall population over time. For instance, it was noted that in the exponential model growth, population does not affect Ppgr, due to the fact that the population will continue to grow despite it all. In order to determine the method that is the best fit for the U.S. Census, it was necessary to consider the population when it was either very small or when it reaches the limiting population L. By doing so, we are able to come to the conclusion that the exponential model represents the U.S. population most accurately, and the Gompertz model is the least accurate. In addition to the methods used, ordinary least squares is another method to figure out which of the models is the most comparable to the U.S. Census. Given more time, we could have come to a conclusion based on ordinary least squares method, which would have been the most accurate method to use.